We are covering thermal stress and strain, a key topic in the Mechanics of Materials section for the FE Civil exam. Imagine a steel beam sitting in the sun. As it heats up, it wants to get longer. This change in length or strain is called free thermal strain. You can find the formula in the Mechanics of Materials section of your NCEES FE Reference Handbook. It's epsilon sub t equals alpha times delta t. Here, alpha is the coefficient of thermal expansion, a material property you'll look up in the handbook's tables. For steel, it's about 6.5 times 10 to the minus 6 per degree Fahrenheit. Delta T is simply the change in temperature. The critical thing to remember here is that if the beam is free to expand and contract, there is absolutely no stress induced. It just gets longer or shorter. This is a classic exam trap. If a question describes an unrestrained member and asks for thermal stress, the answer is 0. Now, let's introduce the core of the problem type you'll see on the exam. What if that same steel beam is wedged perfectly between two massive, unmovable concrete walls? When it heats up, the walls prevent it from expanding. This constraint is what generates thermal stress. The beam is pushing against the walls, and the walls are pushing back, creating an internal compressive stress. The formula for this stress, also in the handbook, is sigma equals E times alpha times delta T. E is the modulus of elasticity, another material property. For A36 structural steel, a common material on the exam, the modulus of elasticity is 29,000 ksi. Notice the sign convention. A temperature increase, or positive delta T, leads to compressive stress because the expansion is being resisted. Conversely, if you cool the beam, it will try to shrink, but the walls will hold it in place, creating a tensile stress. Let's walk through a typical exam problem. A 30-foot-long A36 steel beam is installed between two rigid supports at 50 degrees Fahrenheit. The question asks for the stress in the beam when the temperature rises to 120 degrees Fahrenheit. First, identify your givens. The length, 30 feet, is actually irrelevant for calculating stress, which is a common distractor. You need the temperature change, delta T, which is 120 minus 50, or 70 degrees Fahrenheit. Next, you go to your NCEES FE Reference Handbook. In the Material Properties tables, you'll find the modulus of elasticity, E, for steel, is 29,000 ksi, and the coefficient of thermal expansion, alpha, is 6.5 times 10 to the minus 6 per degree Fahrenheit. Now you plug these into the stress formula. Sigma equals E times alpha times delta T. That's 29,000 kips per square inch, times 6.5 times 10 to the minus 6 per degree Fahrenheit, times 70 degrees Fahrenheit. The units for degrees Fahrenheit cancel out, leaving you with kips per square inch, or KSI. The result is 13.2 KSI. Since the temperature increased and the beam was constrained, this is a compressive stress. The most common trap is confusing problems that have a small gap. If the beam can expand a certain amount before it hits the wall, you must first calculate the total free thermal expansion, then subtract the gap distance. The remaining deformation is what is resisted by the wall, and that's the value you use to calculate the stress. Here's a simple way to remember the core concept. No constraint, no stress. Think of it like being in a crowded room. If you have space to move, there's no pressure. But when the room is packed and you can't move, that's when you feel the stress. The constraint creates the stress. For free practice questions, AI-powered explanations, and more exam prep tools, visit openexamprep.com. That's openexamprep, all one word, .com.